By controlling natural phenomena, we create technologies that transform our world. For example, fire is the control of matter, electricity is the control of charges, and internet is the control of light. And at this moment of human history, we are seeking the control of quantum interactions. When charge, light, and matter interact at the quantum scale, they can form materials with exotic properties that solve the grand challenges of the 21st century. For example, photovoltaic quantum materials can be used in energy, superconducting quantum materials can be used in medicine, and topological quantum materials can be used in computing. The properties of these quantum materials are determined by the underlying quantum interactions, which are described by the diagrams developed by Caltech's famous professor, Richard Feynman, where each line represents a single quantum particle in the material, and each intersection of the lines represents an interaction event. There are infinitely many diagrams of quantum interactions happening anytime and anywhere inside the quantum materials. However, they occur at such a tiny scale that even the most sophisticated instruments can have a hard time detecting them, which limits our understanding and imagination of their application potentials. This is why I'm passionate about simulating quantum materials. To stand on the shoulders of Mr. Feynman, to provide first principles understanding to quantum effects, and to bridge the gap between nature and technologies. To simulate quantum materials, we first solve the Schrodinger equation for each quantum particle, and then we calculate the equation that describes each interaction diagrams. Finally, we sum up as many diagrams as we can to make accurate predictions to the quantum material properties. Since we are investigating real materials, there can be millions of particles and so millions of equations to solve. This is why we use supercomputers to run our calculations, where we leverage many CPU and GPU cores to accelerate our calculations. In the past 5 years at Caltech, I have focused my research on simulating the quantum interactions between electrons and phonons, which are the quantum particles of atomic vibrations. Since then, I have made predictions to the electrical, structural, dynamical, and spectral properties of various kinds of quantum materials. My research has provided insights to decades-old quantum materials problems, like charge transport in organic crystals and high-temperature superconductivity. And today, I'm still thinking about developing new computational tools to simulate the diagrams, to predict material properties, and to bring blueprints to the next generation technologies. With this said, I hope you're as excited as I am about simulating quantum materials and transforming our world. I am Benjamin Chang, and I thank you for listening. Thank you.